Again, Trent Parado, Public Affairs Officer with NASA's Science Mission Directorate in Washington, D.C. I'd like to welcome the Tweeps here back to the tent for the Juno Tweetup, and I'd like to welcome all of you joining us online, virtually, for the conversation. Again, you can follow what's happening on Twitter at twitter.com/NASA-Tweetup, and please follow the hashtags NASA-Tweetup and hashtag Juno. We have an exciting program for you today. We're really excited to have a number of brilliant speakers doing amazing things in our solar system, and we're going to cap it all off with a launch tomorrow, hopefully, of the Jupiter spacecraft. I'm sorry, the Juno spacecraft to Jupiter. So we have a packed agenda. You only get to see this once, Juno going to Jupiter, so get ready to drink from the fire hose, because we have a very exciting and jam-packed program for you today. A lot of people ask us who all is involved in the social media side of NASA. There are a few of us, you've met most of us in this tent, but we feel like it includes all of you too. I mean, it's your space program. It's a real pleasure and it's an honor to bring such a diverse group of people together here and online, and a big shout out to all the Tweeps who've joined us before for Tweetups, and we know that you're out there, so a big hello from us. This is an ongoing conversation, but it's a thriving, dynamic community with NASA Tweetup, and it's fun for us to watch the conversation develop, and we just want to thank you all for helping us tell the story of this remarkable spacecraft, this amazingly beautiful mission, and all the cool things that we're going to discover because of it about Jupiter and about the history of our solar system. So, with that, I just wanted to introduce, again, Stephanie Shearholtz, who's NASA's social media manager, to tell us a little bit more about that, and then we'll get our program underway. Stephanie.
Thank you, Trent. Thank you all for being here and making your way here. It's a great honor that you guys traveled from all over the world. We have people here from 6 different countries and from 28 different U.S. states, plus the District of Columbia. And that's just great that you guys are getting it out to your communities, the places that you live, the people that you interact with, and sharing what you're experiencing here today. We can't invite everybody who registered, so it's great that you can share your experience with everybody else. This is the 23rd NASA Tweetup. We're very proud of what this has become and how your enthusiasm for this event and for experiencing NASA in a very real way has led to more and more Tweetups. Every single one, we think, we don't know if we're going to be able to hold another Tweetup, and you all are so enthusiastic that we find a way to make it happen, and we're so thrilled that we can do that, that we have great support at NASA for engaging on social media and for bringing you out to experience these types of events and launches and NASA centers. There are 10 NASA centers across the country, and there's a lot that you can experience with NASA. We're very active, and so thank you for being a part of the community. You are now we have more than 2,000 people who have attended different NASA Tweetup events. So you're part of a big community and a big family, and even more who've registered online who haven't yet been selected, but who probably will be someday, hopefully. And you all can, it's your community, you own it, you can create it. There's a Wikipedia page that you guys made. There's nasatweet.com, which is a wiki page that you created, which is all sorts of good information, really just if you're a space geek. So, you don't have to be a space geek or a diehard space fan to come to a NASA Tweetup, but we hope you are when you leave. Thank you. We have a great program, really great speakers, and we hope that you enjoy the day.
Thanks, Stephanie. Just a little context quickly. Stephanie mentioned the NASA centers. NASA's broken out into 4 mission directorates as well: space operations, aeronautics, exploration systems, and science. So you're going to be hearing people from science that work with and through the Science Mission Directorate. That's broken out into 4 divisions. That is Earth science, heliophysics, study of our sun, planetary, and you're going to be hearing from people who work with the planetary division today, and astrophysics, everything beyond our solar system. I'm the Public Affairs Officer for Astrophysics. If you have any questions during the Tweetup, be happy to answer them about those missions. Our first speaker is the Deputy Director of the Planetary Science Division at NASA headquarters. He is responsible for the day-to-day program management of the missions, which is the cost, the schedule, the technical performance on every planetary mission that's conducting outstanding and astounding science and making the new discoveries that just keep us all in awe. And on a personal note, this wouldn't have been possible without him, and it's, the fact that we're all here is due in large part to his support. So with that, let me introduce Dr. Jim Adams.
I think Stephanie took off with the handheld mic, because I don't like being tied here. Indeed, the Tweetup in planetary science. Oh, thanks, Stephanie. Appreciate that. The Tweetup in planetary science was kind of an unheard of thing, and I'd been sort of watching it and trying to figure out what was going on with social media ever since Mars Phoenix landed. And when we got to figuring out what we were going to do for guest stops for Juno, somebody on Twitter, I forget exactly whom it was, asked me to consider holding a Tweetup for Juno. So we did a little investigation, and Stephanie came by and talked to us about what they've been doing on STS for that. And we found out that, that it was really quite an easy thing to pull together because the community really self-energizes. And so I said, well, let's do one for Juno and Grail and MSL. And I think we might have... I think Stephanie might have fainted at that point. Because, you know, in just a month's time, we're going to be back here again with 150 of your colleagues tweeting about the moon and the fantastic things we have going on at the moon. I had been thinking about what to say, and so I asked Stephanie, how many slides do I get to show? And she said, none. And so I have no prepared remarks, other than to say it's just a fantastic opportunity, or a fantastic time to be here. Juno has been 10 years in the making. It's going to take another 5 years to get to Jupiter, and then, as Steve will tell you later on, the science starts. So it's been a long haul for Juno. I just came from watching the rocket roll out, got to walk in front of it. It was way cool. Way cool. It's an incredible machine, the Atlas V. And it marks the start of what we've been terming the launch phase of the year of the solar system. The year of the solar system started about a year ago when we realized that we had about 9 events all stacked up inside 26 months. 26 months is a Martian year, hence the year of the solar system. And it has been an incredible ride that started in November with the flyby of the epoxy spacecraft with the comet Hartley 2. We found out amazing things about comets that we didn't expect that we would find out. We returned to the comet Tempel 1, the one that Deep Impact knocked a hole into, and tried to peer down inside the crater that we thought we made, and remapped the back side of it since we didn't get that data the first time. For the first time ever, we put a spacecraft into orbit around the planet Mercury, and for the next year or two, we will unlock some of the secrets of that mysterious planet. And then just 2-3 weeks ago, the Dawn spacecraft got into orbit around the asteroid Vesta, and some of the images, if you haven't seen them, are just stunning. It's going to keep planetary scientists busy for a long time, especially the geologists, trying to figure out what was going on when that body was formed, and what does it mean for the rest of the asteroids that we might explore in the future. But this is the launch phase. So now Juno launches, and then Grail, and then MSL, and then we have a little bit of a hiatus, and then MSL lands about this time next year. And we're just outrageously happy that we're here, we're on schedule, we're on cost, which is one of my biggest worries. And most of all, we haven't compromised the science. The science that we do helps us understand our place in the universe. And that's a big challenge. And every time we begin to ask a question and answer a question, we have more questions. That's what the scientific process is all about. And that's one of the reasons why we do what we do, because we're searching for our own place in the universe. I think I'll stop talking and just answer questions, if that's okay. Do I have time, Stephanie, to answer questions?
Yes, certainly.
Okay. So, are there questions?
Raise your hand. Jason and I have microphones. We'll come around.
No questions.
So I have a question.
Sure.
Are we going to launch tomorrow?
Oh, good question. Anybody got a friend named Emily? Are there any Emilys here? So we decided this morning at 6:30 to go ahead and roll the rocket out to the launch pad so that we could be ready to launch tomorrow. The next decision point is 6:30 tomorrow morning when we decide whether or not to start the terminal count. That will be based on the status of the weather and a number of other things. We'll get into the Okay. Anyway, the countdown starts after we make a decision at 6:30 tomorrow morning. In the middle of that countdown, at about 9:45, we'll make a decision about whether or not to load cryo. When the cryogen gets loaded, if there's a scrub, it takes about 26 hours before the rocket could return to the safety of the vertical integration facility. So the real issue is not, is the weather going to be good enough tomorrow to launch? The real issue is, after we load cryo, will the weather be good enough that we could return the spacecraft to the vertical integration facility? And that's really the big decision that we have ahead of us. Right now, I'm proud to report that everything looks go for launch. With the one caveat that Emily just won't make up her mind on where she wants to go. So we'll see how that goes. But it's going to be a fantastic launch. It's this, like I've told people in the past, this is the largest of the Atlas V family. It's the Atlas V 551. That means it's got these 5 enormous solid rocket boosters strapped to the sides of it. And it's going to jump off the pad. Some of you have probably seen Atlas V's before, but you've not seen this one unless you were at the New Horizons launch, because this is only the second one in history to fly. So, any other questions?
So you're going to tweet at 6:30 tomorrow morning whether we're on track. So everybody follow at NASA Jim.
Well, we'll see. I will tell you that I will definitely, if there's something to tweet, I'll put a notice out.
Awesome.
So we got a question over here on your right.
Sure.
That's right, over here.
Which right? Oh, there we go.
Hi, NASA Jim. I'm Dave.
Hey.
So it seems like to me there ought to be a rocket load of data coming back from all this. What happens to that data? Where does it go? Who uses it? How
Okay.
are we going to solve all our world problems with
So
that?
the data that comes back, it takes, first off, the light time. Lots of people ask, what's the light time? How long does the data transit from Jupiter back to the Earth? It's about 48 minutes, depending upon where we are in the year. But every bit of data that comes back for planetary science goes into something called the Planetary Data System, which you could Google right now and has open access. You could go to the Planetary Data System and pull up the data that's been formatted and loaded into the PDS. Will you find the latest images of Vesta there? No. Will you find the latest MRO image there? No. It lags about 6 months. And the reason that they lag about 6 months is so that they can calibrate the data and validate that they've actually got the formatting right and the captions correct and that sort of thing, because then it is public. And it goes out, and we just don't control how it's used. So, open data. Who's directing questions? Not me, right? All right.
Question on the left over there.
Good.
Earlier, you were speaking about how questions drive science and how we're always trying to find more answers to those questions and things. And it occurs to me that for those of us who don't, launch rockets for a living, the idea of a rocket scientist is usually held up as a cliche for somebody who has all the answers to these really difficult questions. I was just wondering if you could speak to the idea of certainty in a mission like Juno. Where's the balance between what we know is going to work and what we don't know we're going to find and that sort of thing? How does that play out in these missions?
Well, I don't know if I'll answer your question, but it certainly brings up a lot of thoughts in my mind. There are 3 major questions that planetary science, and indeed most of NASA science, seeks to answer. The first is, how do we get here? And the second is, where are we going? And the third is, are we alone? And frankly, everything that we do in planetary science is driven by one of those questions. One of the really interesting things is, you start breaking it down. You say, okay, well, are we alone? What does that mean? Are there amino acids elsewhere in the solar system? Turns out the answer is yes. What is going on with the methane on Mars? And why does Titan have so much methane? It rains methane instead of water there. And why does Europa have so much water when it's embedded in this radiation belt? These are questions that scientists like Steve Levin, like Scott Bolton, ask and answer, and then generate more questions. In the search to find out, how did we get here? Where are we going? And are we alone? Really, our place in the universe. One of the really interesting quotes I love is Neil deGrasse Tyson was being interviewed by Jon Stewart on The Daily Show. And he said, that's the problem with all you scientists is you got too many questions. And Neil deGrasse Tyson said, no, that's the seduction. And he's absolutely right. Learning about something causes you to want to learn more about something. And that's really the mode that we're in. And I'm hopeful that that inspires a younger generation to move into science and math and technology so that in the future, we will have a space-aware, an active space-aware generation.
Next question's over here on the right.
Barbara Buckner, B. Buckner, how close do you think we are to the 10,000?
Oh, how close? Anybody want to hazard a guess? 150. Is that how many you think are attending, or is that how close we are? I already told somebody, so you guys over there at Tim's table, you can't answer. So here's the way it breaks down. There are 3,000 invited VIPs that will be at Banana Creek. Delaware North will sell 2,000 tickets for people that will also go to Banana Creek. Those are all confirmed. There are 150 Tweeps. There are 300 people that will be in OSB 2. There's going to be 1,600 people at the Turn Basin. If you total all that together, you get somewhere in the neighborhood, and somebody would have to do the math for me, 6,000 to 8,000. There are close to 2,000 more people that will be watching the launch outside the gate of Kennedy Space Center. And so we believe that we will break the 10,000 mark. That's what the guest operations director reported at the Launch Readiness Review on yesterday. So I thought on my way over I might tell the story about how Juno 10K came about. But before I do that, I thought I really need to thank you all for making that happen, because without social media, we would not have been able to do as well as we did in terms of raising the awareness of expendable launch vehicles, their launches, and the missions that they support. So, do I have time for the story, or Stephanie, are you? All right. About a year ago, I was in a meeting, a budget meeting, with Charlie Bolden and Ed Weiler, and Ed Weiler was making a presentation, and his comment was, inside of 4 months, Planetary Science Division will launch $4.5 billion worth of hardware into space. By the way, that's what starts tomorrow. And Charlie just about came out of his chair, and he said, we need to find a way to engage the guest operations and the community down at Kennedy Space Center to embrace expendable launch vehicles. And everybody went, yeah, that's a really good idea. But it means we'll send them a little bit more money. About 3 months ago, it was May, I was in an elevator. You know, they always tell you should have your elevator speech ready. Well, I had been rehearsed, and I was in an elevator with Charlie. And I said, Juno is the first launch after the last shuttle. And I said, we normally invite 300 to 1,000 people to a rocket launch. But you guys, on the human spaceflight side, you'll get hundreds of thousands, or, you know, in the case of STS-135, was it close to 1 million out for a launch? I said, wouldn't it be cool if we could get, and I in the moment made up a number, wouldn't it be cool if we could get 10,000 people out to the Juno launch? And he said, that's a great idea. And then I immediately backed off and I said, well, I don't know if I can do it. And he said, yes, but if you don't try, you won't. And so that's how we got the support not only for Juno 10K, but for the Juno Tweetup and for the Grail Tweetup and for the MSL Tweetup. And so we are going to set similar goals for Grail and MSL. I'm pretty sure we'll get 10,000 for MSL. I'm not so sure, I don't know about Grail, but we won't know if we don't try. So that's where we're at.
And just on that note, you know, Jim's a great guy to ask questions about Grail and MSL too, because he's an all-over planetary guy.
Hi, Jim. I'm Morris Jones from Los Angeles, on Twitter, Mojo LA. And I don't know if this question is in your wheelhouse or not, but I grew up watching, as a rocket geek, watching Mercury, Gemini, Apollo. And I know that after the first two Mercury Redstone missions, John Glenn and all the others rode on a rocket called an Atlas. And I wonder if you could tell me if there's some tie between the Atlas that he rode and the rockets that we call Atlas now.
You know, I really can't answer that question. I know we were talking about it just yesterday, and frankly, I can't remember the answer. But there'll be a ULA person here, right, Stephanie?
We're expecting a ULA person to come talk to us tomorrow.
So if you could hold that question, that is a very good question.
Or you could tweet at ULA launch.
There you go.
So next question over here on the right.
Hi, my name is Emily Carney, and I'm out of St. Petersburg, Florida. I have a question. It's more of an engineering question. I know previous space probes in the past, like Pioneer and Voyager from those families, they used radioisotope thermoelectric generators to power themselves, or RTGs. I know Juno is a departure because it employs solar panels. What was the motivation behind using that, and why, basically?
Oh, you're asking the right guy that question, too. So RTGs is also in my portfolio, as well as the plutonium that powers them. It's a very expensive prospect to fly a radioisotope thermoelectric generator, or its new cousin, something called an advanced Stirling radioisotope generator. I don't even want to quote numbers. It's just very expensive. And so you only ever use it when you're going someplace you're absolutely certain you can't use solar arrays. And so Juno really pushed the edge. We'd not ever been to Jupiter before on solar arrays. We may not ever go back to Jupiter on solar arrays. The Juno mission and its orbit design is just so very highly optimized that you could make solar arrays work. It did come at a cost, though. We invested quite a lot of money in making solar arrays work that far out in space. There's an effect called LILT, low intensity, low temperature, that causes the solar arrays to not function the way they would closer into Earth. And so we spent a lot of technology dollars trying to make sure that we understood those effects so that the mission would be successful. The solar arrays on Juno, they come out right 6 minutes after we separate from the launch vehicle in shadow. And so as we emerge from the eclipse of the Earth, they'll be illuminated by the sun. They'll be full on the sun. They put out about 12,000 watts while they're here at Earth. But during its 5-year voyage, the sun gets dimmer and dimmer and dimmer, such that by the time you get out to Jupiter, it's only putting out 400 watts. And 200 of those 400 watts are used to keep the spacecraft warm. So the whole Juno mission is running on basically 2 light bulbs. So, all right. Do we have time for one more?
Hi, Jim. My name's Jason Major. I'm a space blogger for lightsinthedark.com. And once Juno launches, it's going to take 5 years for it to arrive at Jupiter in July 2016. When would we start to actually see images coming in from Juno? Will it be when it establishes orbit, or will we get a sneak peek as it's approaching?
I'll tell you what, I'm going to let Steve, when Steve Levin gets up and talks,
Okay.
I'll let you poke at him about that. Our intention is that as soon as images are available, we start taking them as long as the spacecraft is safe. And then soon thereafter, we make them as public as we possibly can. But a lot of that depends upon the way the science architecture is set up, right, for the mission. And so Juno's primary mission is not to take pictures. It's to look into the clouds and measure the magnetic fields. Once that data comes back, there's some processing that they have to do before they can say, here's what we're seeing in the clouds of Jupiter, or here's what the magnetic field at Jupiter looks like. There is a camera on board. It's an education and public outreach camera. And I'm not exactly sure how it's targeted, but I'm sure Steve will tell us, right?
And also Mike Ravine will be talking to us tomorrow morning about JunoCam.
Perfect. Yeah.
We'll have a model to pass around.
Excellent. Fantastic. So
One more question.
one more question, and then I'm done.
Questions over here in the back.
Okay.
Hi, John Stockton. And I have a question that's not so much science and more just your personal opinion. You alluded earlier to how, the public is in love with Mars. So MSL is clearly the public favorite. But what is your personal favorite? We've got missions to asteroids, comets, and the moon, and this is cutting out, Jupiter and Mars. We've got all these missions. What is your personal favorite into this?
So my mother always used to say, I love all my children equally much. What excites me is not necessarily the individual missions, but the fact that we can begin to further our understanding of where we're at in the universe. That we can begin to start looking to see if we actually are alone. In fact, Jim Green, my boss, and I have a steak dinner bet on the results of MSL and the classification of the isotope of the methane that we might measure once we land MSL on the surface of Mars. That's a little detailed. But that may help us decide whether or not there ever was life on Mars. So I think that's it, right, Trent? I'm getting the hook.
One quick question, if you can do 20 to 30 seconds on why methane's important. You brought it up a couple times. It's tantalizing as an answer.
Well, methane's a complex organic compound, and it forms in one of 2 ways. It either comes from geologic activity, water flowing across magma, across certain kinds of minerals. You get methane out of volcanoes and that sort of thing. Or it comes from life, either decaying life or excrement, like cows. So what we've seen on Mars is methane clouds that come and go with the seasons. Why is that? We're not sure. Where is it coming from? We don't know. We're pretty sure there's no geologic activity on Mars. Maybe there's cows on Mars. Please don't tweet that. So the bottom line is it's an indicator of life, maybe, and that's why it's important to us. So with that, I've got one thing I want to do before I stand down. Stephanie, would you come up here, please? Stephanie took on the challenge of bringing up a Tweetup from scratch, not just one Tweetup, but 3. And so this is a personal gift from Jim Green and myself to say thank you. And what it is an artist concept, a blown glass of Jupiter. So thank you very much. Thank you.
Let's hear it for at NASA Jim, everybody. Okay, we're pleased to introduce our next speaker. He is the Juno Principal Investigator. He is the Director of the Space Science Department at the Southwest Research Institute in San Antonio, Texas. And then all that means he leads the international science team that's seeking to unmask the mysteries that lie beneath Jupiter's clouds. With that, let me introduce Dr. Scott Bolton.
Well, thank you for being here. It's really exciting. Just one day away from the launch. Juno will launch off to Jupiter. It arrives in 2016. So why are we going there? What's the real reason behind this? So questions, really fundamental questions is what we're after. Who are we? How did we get here? Where are we going? What happened? How did we find ourselves on the Earth? Where did the Earth come from? Where did life come from? These are questions that are addressed by all of the NASA missions, not just Juno. Each one provides some unique piece of information that helps us understand nature, helps us understand ourselves, looking out at the universe, trying to figure out how we fit in. How does the Earth work? How do we work? So Juno, each mission has a unique contribution. Juno has one as well. We're going to Jupiter because it's the largest of all the planets. So after the sun formed, there were leftovers. Jupiter got most of the leftovers. Saturn got the next biggest chunk, Uranus, Neptune, etc. The really tiny scraps are what we are. So we're trying to figure out what happened there. Jupiter, because it's so massive, has held on to its original material. We lost most of ours at Earth. We don't really know our own history very well because we have a powerful enough gravity field to hold on to the material, whereas Jupiter is pretty much the same as when it first formed. I mean, it's got lots of dynamics, the magnetosphere and the atmosphere buzzing around and stuff, but it's pretty much held on to its composition. And we know this because it's mostly hydrogen and helium. In fact, the sun is mostly hydrogen and helium. The interstellar clouds that we see that we think make stars are mostly hydrogen and helium. The whole universe is mostly hydrogen and helium. So there's this other stuff. Cosmologists call it heavy elements. Think of your chemistry table when you were in school. So you got hydrogen and helium, the two lightest elements. The next ones, in fact, all of them are just the heavy elements. The carbon, the nitrogen, the sulfur, the noble gases, the oxygen. So somehow, and they're just traces in the universe. It's mostly still this hydrogen and helium stuff. So somehow when Jupiter forms, it gets a little bit more of these heavy elements than the sun does. So the sun gets formed, Jupiter's almost just like it, but it's got a little more of these heavy elements. We call it an enrichment. We don't know how that happened. We know that it's enriched in carbon and nitrogen and sulfur. In fact, Galileo probe went in and we know that it's enriched by all these things, about a factor of 3 or 4 with respect to the percentage of hydrogen in it compared to the sun. We don't know how that happened. We're missing one of the key pieces, oxygen, which is tied up in water. Oxygen is the third most abundant element in the universe, so we're missing the next biggest piece. It's fundamental to us. We know we search for life looking for liquid water, but it's fundamental in the universe. It's probably the most common molecule. I mean, multi-element molecule apart from H2, 2 hydrogens. 2 hydrogens and oxygen make water. So we're trying to figure out this history. We're trying to figure out where we came from. The stuff that Jupiter's enriched in is the stuff we're made out of. So understanding the history of these volatiles across the early solar system comes back and leads to us somehow. Not just the Earth and the terrestrial planets, but life itself. We don't know the history of these elements. We don't know the history of oxygen. So what Juno's doing is it's going back to Jupiter because it's the biggest and it's got this record for us. It's going to get the oxygen abundance by measuring water deep in the atmosphere, something the Galileo probe wasn't able to get. Even though it worked perfectly well, it went into some weird spot, or at least some scientists believe it went into a weird spot, and the oxygen was deep down, and so it never really got the measurement. Of course, though maybe the scientists are wrong, and maybe that's the way Jupiter really is. So Juno will find out whether that was a weird spot or whether Jupiter's all over like that. If it turns out it wasn't a weird spot that Galileo probe went in, and Jupiter is actually depleted in oxygen, then we actually have no real understanding of how the solar system is made or how any planet gets made. And the scientists are going to have to go back to square one, come up with some explanation of what happened to the oxygen, because we don't know. If it's got a lot of oxygen, it may help us understand where Jupiter's formed. Farther out, maybe out at Uranus and Neptune's distance and migrates in, or maybe it's formed near. These are things that are tied to how much water we find in Jupiter. What else does Juno do? Juno goes into this polar orbit, a very special polar orbit, going right over the poles and very close to the planet, 5,000 kilometers above the cloud tops. So that's pretty much skimming the cloud tops. We do that because we want to measure the gravity and the magnetic field very precisely. The gravity field tells us how the mass is distributed inside the planet. So when we start to put together the ingredient list, we also have sort of the structure of Jupiter to put together into that model of how it forms. It's our example. It must have been the first planet that formed. It got most of the leftovers. How did that happen? How did it get enriched? Does it have a core in the middle? Is there a core of heavy elements in the center? We don't know. Juno will help us constrain that. That core of heavy elements may be something that's kind of like the rocks or the ground that we're used to, but of course it's in the middle of Jupiter under incredible pressure, so it's not going to look like a rock like we know of. It may not have any core. It may just be gas getting more and more pressure, and going through a transition. We know partway down the hydrogen starts to behave like metallic hydrogen, like a fluid. Somewhere deep in that layer, that's already a weird substance, somewhere deep in that layer, a magnetic field gets generated. That magnetic field is the most powerful of all the planetary magnetic fields in the entire solar system. We want to study that. We want to understand how magnetic fields in general get developed. There's a theory out there called the dynamo theory that says how the Earth's magnetic field gets created, but it doesn't work perfectly well. There's a lot of things we still need to learn about it. Jupiter offers a comparative study, and even better, it's transparent down to that metallic hydrogen, whereas the Earth, when we look at our magnetic field, has a permanent magnetized crust blocking our view down to where the core is. What else do? We go over the poles, and we're perfectly situated to study the polar magnetosphere and the aurora, the northern lights. Of course, there's northern and southern lights. We're in the north, so we always call them the northern lights. I've never asked in Australia, but they may call them the southern lights. But anyway, so we go right over the poles. We've got a whole bunch of instruments that are going to study those aurora and look at the particles going up and down the magnetic field lines, creating those aurora. That will help us understand Jupiter's aurora, which we don't really understand very well yet. But we'll also compare that back to Earth and Saturn and start to put together the picture of how aurora and polar magnetospheres work. These are pretty important to us. That magnetosphere around Jupiter is huge, but the magnetosphere around the Earth sort of shields us. So that's a very key thing to understand the physics behind that. And of course, one of the key things that scientists do in order to learn is comparative study. So comparing the different planets is what allows us to learn how the planets work. You look for similarities, differences, and you try to sort out how nature works. So we learn about ourselves by studying Jupiter, but we also learn about Jupiter. We also use that as our example of giant planets around other stars. We're now getting to the point where we can detect other solar systems. We have to understand the role that these giant planets played in creating these solar systems, and so Jupiter is our key to doing that. So So I'm just giving you a quick overview of the science for Juno, and I'll take questions if you guys want. I don't know.
Okay, roving mics are coming.
Donald Schwartz, Iskabibble. My question is, there was mentioned in the press kit that the reason that Jupiter is not a sun is because of its mass. Now, how large would it be? And is it possible that should we need it, could we start it up again?
I'm sorry, what was the last part?
Could we start Jupiter up again without having it be a mass and having it be an alternate sun? Say our sun's going to expand to take us in. So what about Jupiter? Could that be the B plan?
So are you thinking it's not warm enough here right now? Because I'm pretty hot. But anyway, that's a good question. So I've read some of the same stuff, and my understanding is that if Jupiter was about 80 times as massive, and that's what I recall, I may not be completely correct on this, but about 80 times as massive, then it would have been massive enough to ignite the nuclear fusion furnace inside, which is what sort of creates a star, right? And I think at this point there's no way for it to get 80 times more massive, because most of that extra, if I took all the rest of the solar system and put it in there, it still wouldn't be big enough. So now the thing that I'm not sure of about that 80 times is that there are many kinds of stars. And I don't know if the 80 times is to match our star or it is to match the smallest known star. So it's possible that Jupiter missed being a star by something else. But the astrophysicists that calculated that, and I'm not familiar with that calculation directly, is I think that was the minimum mass to get the fusion going. So I don't think there's any way to change that. But that's basically what it is. But Jupiter is still cooling from its formation. And so it's hotter inside than outside. It's glowing. We use that in order to get our water abundance. We basically listen inside the planet with our microwave radiometers. So we're basically just receiving what's called black body radiation. We're just looking at the thermal glow from Jupiter glowing, and we look at it with different wavelengths. So you and I, all of us, if we looked in infrared cameras, we'd be glowing. Jupiter's not as hot as us, so it's glowing in radio. So that's what we're doing. We look in microwave, basically the same kind of stuff that your microwave oven works off of. We're watching this glow, and we have different wavelengths. Some are more or less opaque to water. So things that are more transparent to the water, the longer wavelengths, get the glow from deeper down. And the stuff that is really opaque to water just gets blocked right away, and we see the glow from the top. And that's really the trick to the water abundance. I know that didn't tie to your question, but I thought I'd take that opportunity to explain it. Did I get you all the answer enough? So you're really looking way off in the future and wondering, when our star burns out, could we ignite Jupiter? So I think the answer is no. And it's so far off, I don't think you should lose sleep.
So Arthur C. Clarke was wrong. That's what you're saying. One question over here to your left, Scott.
As you probably are aware, there's a device on Juno called Jedi. Who came up with that name, and how long did it come up? How long did it take for them to come up with that?
So that is the energetic particle detector built out of APL, Applied Physics Lab, which is part of Johns Hopkins University. That name was hotly contested, it turns out. And the reason is that before there was a Juno, before we made Juno, we were proposing looking at other concepts, and one of them was called Jazzy. That was sort of a mission that I'd put together before we put together the Juno concept. And it did pretty much the same kind of thing, but it was just flying past Jupiter instead of going into orbit, so it didn't do as much. And there was a plasma instrument. Plasma is the low energy particles. And then you can have high energy particles. Both are needed to be measured, but you need different instruments. So the low energy particles was being built by a friend of mine at Southwest Research Institute, and he named his instrument Jedi, on the old mission. Then we dissolved that proposal, that concept, and we started Juno. And before he could announce his name again, the guys at APL said, we're naming our instrument Jedi. And I think the name, I don't know the exact person that thought of the name, but I give the credit to a guy named Barry Mock. But it may have been somebody that was part of his team.
Thanks, Scott. We'll take one more question and do it over here.
Okay, so besides the hardware working and getting delivered to Jupiter, what are the top 2 mission success criteria for Juno?
To be successful, besides the launch? Okay, so I get a free pass that I'm already at Jupiter and everything's working. Okay, so for the science mission, there's three most important measurements that we really want to get. We want them all, of course, but just probably the highest level science goals are the water abundance inside Jupiter, the global water abundance. So we look at many different places to get that. The gravity field to constrain whether there's a core in the center. These 2 things are the 2 most important measurements to discriminate among theories of how planets are made. We're trying to figure out the recipe for planets. So those are the 2 pieces of information that are probably the most important to help us in discriminating among theories on that. The third most important measurement that's probably equal with these is the magnetic field. And that's because it all ties into the internal structure of how Jupiter's built. The internal structure meaning the internal magnetic field. And that's why we go so close. So I would say that those 3 measurements are the 3 most important. Now we have official success criteria that deal with being able to obtain 4 data sets out of 5 data sets that we collect. So we want to do a little bit better than what I just named.
Okay. Thanks very much, Scott. Appreciate your time. Good luck tomorrow.
Thank you.
Okay, I'm pleased to introduce our next speaker. This is excuse me, the Juno project scientist at the Jet Propulsion Lab, Steve Levin. When we see Jupiter, we see this. I mean, we see these remarkable images. We see the big spot. We see something incredible. I think Steve, it'd be fair to say, sees not only that, but the magnetic fields and the synchrotron emissions and everything that tells us such an incredible story about this iconic planet. So it's a pleasure to have you here. Dr. Steve Levin.
Thanks. Well, I'll hold this one. It's easier. So basically what I want to do is answer questions. And first, I'll tell you just enough so you know what to ask questions about. And the first description of that is you can ask me anything because I've learned how to say I don't know or I don't want to tell you. So ask me anything you want. But what it would make sense to ask me about is the science on Juno. And I'll tell you, I also, one of my main jobs, I like to think of it as translating science to engineering and translating engineering to science. I kind of help do the interface between the engineering team and the science team a lot. So you could ask me about that too if you want. I'm sure after what Scott said, there's plenty of questions. So why don't we, yeah.
Okay.
Oh, I guess we got to wait for the mic, huh?
I asked this question of Jim before, and I know the camera aboard Juno is he said a public outreach camera.
Right.
But obviously with all that we've been waiting for to get to Jupiter in 2016, what type of images can we expect from the Juno spacecraft? Obviously,
Cool.
it's going to be very close to Jupiter.
So first of all, I want to make sure I make the point, because it's important to me at least. We get a lot more information back than just images. Right. So everybody, when you do a space mission, one of the things everybody wants to see is the pictures. And I understand that. We're used to looking at pictures. But we have a lot of ways of looking at Jupiter, and pictures are only one piece of it. Having said that, JunoCam's going to take some really cool pictures. So what's going to happen is JunoCam is sized and aimed at taking pictures of the poles. We haven't had a spacecraft come anywhere close to Jupiter over the poles. So if you go look at images we have of Jupiter, some people put together, a montage or whatever and make a globe of Jupiter. We have one over there or whatever. And you look at the north and south poles, they're kind of blurry or blank. That's because we don't have any good images of them. We're going to fly, Juno's going to fly right over the poles. JunoCam has a big, wide, 50-something degree field of view designed so that when we come over the pole, really close, it'll get a really nice image. What we're going to do with that is we're going to, between now and 2016 when it gets there, set something up so the public can have lots of input on which pictures we take. Because you can't, the camera can't continuously take pictures, both because it needs some time in between for the camera and because you'll have limited data link all the way from Jupiter. So we'll have to make decisions about which pictures to take, and we'll get the public involved with that. And then when the raw data come down, you have to take that data and turn it into good quality images and stitch things together and stuff like that. And we'll let the public get involved with that as well. So not only will it take really cool pictures, but there'll be an opportunity to play with it. It should be really fun. I don't know who's got, I'll let whoever's got the mic should be choosing whose questions. Yeah.
Kind of an engineering question. Could you comment at all on the how the solar panels are being protected from Jupiter's electromagnetic fields?
How are the solar panels protected from the radiation? Is that what you're asking? Yeah. Well, the short answer is they're not that protected, but they've got a thin layer of cover glass on them. We've done lots of tests to understand how they will behave in the radiation belts and how much degradation they'll take over time and so forth. So we calculate how much power we're going to lose and make sure that we've got enough extra solar panels so that by the end of the mission we still have enough power. You have to worry not just about the radiation, but it's the low intensity and low temperature as well. Solar cells behave differently at lower temperatures than they do at room temperature, and they behave differently in low intensity. If the light's not as bright, you obviously get less power, but the efficiency changes too. So we have solar panels. We're intending to handle that. We've done a lot of tests with them to try to understand what the radiation will do to them, how they'll behave in low intensity and low temperature. And of course, we select the solar cells a bit too. You don't just go down to the store, buy a zillion solar cells and put them on the arrays. You go to, obviously, Lockheed did this. They go to their subcontractors who can give them the best solar cells, and then they screen them. So you look through them and you come up with tests to test a solar cell to see how it's going to behave in low intensity, low temperature, and radiation, and choose the best ones to put on the spacecraft. And I'm looking for...
NASA is made up of amazing people that perform magic. I mean, you guys just... you do things that nobody would ever think of, but at some point, a decision has to be made, and this isn't really a Juno question, this is kind of a spacecraft question. At some point, a decision has to be made to figure out what we're going to take. And when, the point came up earlier that when you get to Juno, we're going to have 200 watts of power to use. So how do we decide what experiments are carried along and what missions? I mean, is there some kind of an engineering death match where people say my idea is better, and how do we decide what goes to get the best bang for the buck?
Okay, so I'll give you the really short answer first, and then I'll explain. Okay, so the really short answer to a question like that is Scott Bolton decides. Okay, but the longer answer, he doesn't just do that in a vacuum and make it up. We have a team, and generally we get a decision like that by consensus. What happens is, very early on in the process, when we're working on the proposal, right, we looked at what science we're trying to do, what NASA has said they're interested in based on the decadal survey and other scientists coming up with what are the important questions, what we think we can do, how much power we expect to have, how much of all the other resources we expect to have, and we try to work it out and get investigators involved. And yeah, you can build an instrument a lot like this one, and if we do this to it, it'll have a little less power, and oh, if you do that, you can add a little more there. You work that out as a team and come to a consensus about what things are in the proposal. Then after we got selected, we made a few changes as other things came up. For example, the Italians weren't quite able, at the time of the proposal, to contribute an infrared imager and spectrometer. But not very long after the proposal, they said, yeah, we've got the funding on our side, we can do this. And so we had a discussion within the team about, can we afford to add them? Because even though they were going to supply it, we didn't have to pay them money for it. We still have to pay resources on the spacecraft to supply it with power and a place to put it and radiation shielding and all that stuff, right? So obviously it's on board. The science team and everybody else concluded this is really worth it. This is a great instrument, so we added it in. That kind of thing happens for all kinds of decisions. Big ones like adding or subtracting an instrument, little ones like, you know, can you put an extra cable for this thing and have it be dual-sided and have a little redundancy on it? Or there were a couple of times where we made the solar panels bigger, and we had a big internal discussion about the pros and cons of making the solar panels bigger. That kind of stuff, those are called engineering trade studies. Generally speaking, what happens is that's handled by the project system engineering team. So it's mostly the engineers who work out what you can do and what you can't do and the pros and cons, and they come to the science team and say, how important is the science you get from this? And they lay it all out for the team. We try to arrive at a consensus, and if there isn't a consensus, Scott decides.
So we got time for 2 more questions. One of them's right here.
Oh man, already?
Hello. My name is Lisa Johnson, and I happen to be working on a satellite that's going to be trying to dissipate some of the high energy particles that we have here in the Earth's atmosphere. So I was curious about Jupiter's auroras and how do they compare to the Earth, because the Earth much closer to the sun. We have a lot of the solar wind particles that get in that cause the great auroras that we have here. Jupiter is much farther away, and it also doesn't have the human contribution. So I'm curious what we will see on Jupiter and what data we're going to be measuring.
So first of all, that sounds like a really cool experiment. But the way you have to picture this is the aurora, and here's Fran Bagenal, who is the person who should answer this question. You want to just come do this? I could give you a great answer, but Fran is like the world's expert on this.
Okay. So indeed, we're going to be measuring the aurora, and but not just looking down on the aurora with the UVS and with GRAM and looking at the radiation, the UV radiation and the infrared radiation that comes from the atmosphere. But we're also going to be looking at the particles that are causing that radiation. So we got a problem with radiation. Have we sorted out radiation and radiation? Okay, so we have to sort out photons, which is the UV particles coming out and the infrared particles coming out, and the electrons and protons which bombard the atmosphere and generate that light to come out, okay? So infrared and UV light come out that we detect with GRAM and UVS, and that'll show us what the aurora are. But also, we will be carrying 2 instruments that measure the energetic particles, the JEDI and JADE instruments, that are the particles that are coming in and bombarding the atmosphere. And then on top of that, we have waves, which measures electric fields. And my hands go like this because I'm thinking wiggling fields, right? You know, so electric fields and magnetic fields, MAG doing the magnetic fields. So what we think is happening is that we have waves in literally electromagnetic waves at fairly low frequencies compared with light waves that scatter particles, accelerate particles, and we think that then those accelerated particles come bombarding into the atmosphere, excite the atoms and molecules in the atmosphere of Jupiter that then glow with this infrared and UV radiation. So in some ways, it's almost exactly the same as the northern lights with the Earth, where we have the same sort of processes going on in the northern poles and the southern poles producing that process. What we don't know, and this is the big difference between the Earth and Jupiter, is where that acceleration process happens that excites those electrons that bombard the atmosphere, and what are the causes. Because with the Earth, we know that the solar wind bombarding the Earth's magnetic field wheels it about, makes it shake, and that's what causes the particles to be accelerated and then ultimately hit the Earth's atmosphere to make the aurora. And so the Earth's aurora very strongly depends on what's going on the sun and what comes from the sun and hits the Earth. Now with Jupiter, the magnetic field is so strong that it holds off the solar wind for a long way. Okay, so at Earth, towards the sun, the solar wind, in the solar wind direction, the Earth's magnetic field extends for about 10 times the radius of the Earth. So you think of the Earth and then something 10 times bigger. That's the size of the magnetosphere of the Earth. With Jupiter, and remember that Jupiter is 10 times the size of the Earth, so you could put the magnetosphere inside the planet Jupiter, the Earth's magnetosphere within the planet Jupiter. Jupiter's magnetosphere is 100 times the size of Jupiter. That's just in the direction towards the sun. In the direction away from the sun, it goes past the orbit of Saturn. So this is a vast region. So the processes are very different. It's not affected by the solar wind. It behaves on its own due to what's going on inside. So has anybody talked about EO and that pesky little moon EO and what EO is doing? You won't. It's mine. Anyway, we can talk about pesky little EO later.
She was asked about the size, too, of the aurora on Jupiter being so much bigger.
Right.
I think we haven't really talked about why they're bigger.
When you say bigger, do you mean bigger as in spatially bigger or covers more of the planet? It's about the same size on the planet. If you were to draw just a sphere and draw where the aurora are for Jupiter and where they are for the Earth, they're not all that different. About the same. But they are brighter on Jupiter.
I promise I'll give up the mic again when they make me.
We've got time for one question for you back here. Yes.
Okay, it's a slightly less technical question. Where do we get a shirt like that?
Am I allowed to mention commercial companies? It turns out Land's End will do. They have like a business corporate section or something, and if you give them a logo, they'll make shirts. So Scott got this stuff and gave it to them, and then team members can just call them up and say, you know, number whatever I want, logo number whatever on my shirt, and I have about 10 of these. But we're going to do Juno glitter tattoos too. So. Okay.
Thank you, Steve. Really appreciate your time. Let's give a big warm. Okay, so for our last tweet up, the big challenge is it nearly turned into Space Woodstock outside with the rain and the mud. And I think our bonding experience is going to be Florida in August. And I know it's getting warm on this side of the tent, especially because the sun is... So keep hydrated, please. If you need some water, find one of us in a blue badge. Let us know. That side of the tent, because it's a little more out of the sun, is a little cooler. So if you need to stand up, go over there, stand by the air conditioners. I understand. We're going to keep moving along if you guys are still in it with us. All right, fantastic. So it's my pleasure to introduce 3 of the Juno science team members that are going to be working deep down in some of the scientific discoveries that Juno is going to enable. And they are Toby Owen, professor of astronomy at the University of Hawaii. Fran Bagenal, who you all just met. She's professor of Yeah, please. No, Fran, absolutely. Professor of Astrophysical and Planetary Sciences and faculty associate of the Laboratory of Atmospheric and Space Physics at the University of Colorado in Boulder. And Dave Stevenson, the George Van Osdol Professor of Planetary Science at Caltech. So we'll get everybody up here. Thanks. Great. Take this badge in your pocket if you would. Thanks. So we're going to share the microphone for now, and I'll try to get you the other 2. Whoever wants to speak first.
Okay.
Yeah?
So you've already heard what I'm interested in. I'm going to hand the phone over to these guys. The microphone.
So for me, this mission is very exciting. In some respects, a culmination of a career, because 40 years ago, when I was a student at Cornell, I embarked on a thesis, the title of which was The Interior of Jupiter. And now finally we're going to find out the truth. But it's too late for them to take away my degree. A planet is like a book or a movie. It tells a story. It has a plot. And in particular, it tells you something about history. When you look at a planet, you're not just looking at the way it behaves now. You're looking at the outcome of an evolution over the age of the solar system, 4.5 billion years. And particularly in the case of Jupiter, you are seeing information about how the planet formed and how it has evolved. And Jupiter is the 800-pound gorilla in the solar system. It has affected the architecture of our planetary system. It has even affected Earth. The water that I hope you're drinking very likely came from a region near Jupiter. And the way in which it was delivered is affected by the way in which Jupiter is formed. And that process of formation is there as a memory in the internal structure. One of the central questions of the Juno mission is to understand whether there is a central concentration of heavy elements that Scott Bolton talked about, material that on Earth would make up a rock, maybe ice. The amount of that material, the way in which it's distributed, is a legacy of the formation process of the planet. So in our solar system, the place you look to understand these processes is Jupiter, because Jupiter is the most massive planet. You might also say, let's look at the Earth, and people do look at the Earth, but the nature of Earth itself is affected by the structure of Jupiter. So the exciting thing about this mission is that it will bring three important things that Scott Bolton mentioned to bear on this question. Water. Water is extremely important. Toby will say something about that as well. The amount of water, the origin of that water is of central importance for understanding the nature of Jupiter. The gravity field, which will tell us something about how the materials are distributed, and the magnetic field. Now, I want to say a few more words about the gravity field and the magnetic field. The gravity field, of course, is determined by looking at the trajectory of the spacecraft, which will be slightly disturbed by the distribution of mass within the planet as it goes around in its orbit. The orbit will be ever so slightly modified, and that will show up in the Doppler signal that comes back to Earth. And in addition to learning about the central concentration of matter, the gravity field has the exciting prospect of telling us about some aspects of the outer part of the planet as well. It may, amazingly enough, actually tell us something about the nature of the winds on Jupiter. On Jupiter, we have these very strong zonal winds. There's an equatorial jet and more complicated structure at higher latitudes, and those winds change the shape of Jupiter and thereby change the gravity field, and we hope to pick that up. And that will be exciting because there's a possibility of learning about the depth to which those flows extend. At the moment, that's a total mystery. With the magnetic field, as Scott Bolton mentioned, there is the prospect of learning about the nature of how magnetic fields are generated within planets to a greater extent even than Earth. Because on Earth, we have the problem that the measurements we make at Earth's surface or in space are affected by the presence of magnetization in the crust. Jupiter has no crust. It has a region of metallic conduction that extends out to perhaps 80% of the radius of the planet, and within that fluid, the field is being generated by a dynamo process like that in Earth's core. We would like to understand that process better. Now, I want finally to make a general comment about planetary exploration. People often say, well, what's the most important thing that a mission is going to do? And my answer to that question is, the most important thing is the things we cannot predict. For indeed, if you look back at previous missions, if you look back at what Voyager did, arguably the most successful mission ever to the outer solar system, 2 spacecraft, or if you look at what Galileo did, or if you look at what Cassini is doing, the most important, most exciting things that came out of those missions were the things that we did not predict. And I think that will be the case with Juno as well. The most exciting things that will come out of this mission are the things that I and nobody else on the team can predict. Let me, Toby, you want to talk for a while?
Maybe you want to answer questions.
Or we could do questions as a group, or I could answer questions right now. Yes. Any questions?
Okay, we got a question over here on your left.
Hi, I'm Kat Robinson from Tucson, Arizona. I have kind of a question for all of you. I think one thing that's been mentioned several times here is the importance of getting the younger generation invested in space and space exploration. So I'm just wondering, what was it that got each of you hooked into space, and what led you to be on this Juno mission?
In my personal case, I went to Cornell, and I went there intending to be a theoretical physicist. And in fact, my PhD is in theoretical physics. But I did take a course from Carl Sagan, and he was an important influence. There were other influences as well, but it was, to be frank, a matter of luck.
Okay, next question is going to be here in the middle.
Hi, Morris Jones from Los Angeles. Over the past few years, we've had the serendipitous opportunity to see Jupiter get whacked by asteroids or comets. And we've seen those scar impacts. And what I wanted to know is if those events, as unpredicted as they were, or we saw Shoemaker-Levy coming, if what those might have contributed to what we know about the interior of Jupiter now.
It turns out that in the impact of Shoemaker-Levy, the material that was excited was very close to the surface of the planet, very close to the region that we can observe from Earth. And so although some of us thought that you would learn about the interior, in fact, unfortunately, those impacts did not tell us about that. It did tell us some important things about waves in the atmosphere, and also some important things about what generally happens during an impact event.
Hi, Alyssa Frankel, Washington, D.C. I know there's a lot that we don't know yet, and a lot that we're hoping to find out in 5 years about this whole core of Jupiter. But what did you write about in your thesis concerning that?
What?
What did you write about in your thesis?
What?
Concerning
Well, in my thesis work, the main thing I actually looked at was the question of whether there is helium rain in Jupiter. And it now seems likely that the answer is yes. And that has been an exciting outcome over many years, because it turns out that that process of forming droplets deep down inside Jupiter also affects other noble gases, especially neon. And it may also be an important energy source for the heat that comes out of Saturn, perhaps less so for Jupiter.
We got a question here in the back.
Hi, my name's BJ Price. I'm from Orlando, Florida. I wanted to ask you about what's it like to work on a project that's so long in the making and so long from 10 years to develop, another 6 years before you're going to see any data. It's an incredible investment of time just to get your experiments to work and to get some data back. What's it like working on an experiment of that duration?
You know, there's an interesting thing about that very long time scale. When I first got involved in this mission, I had a mindset that I didn't want to be involved in missions. I was just happily sitting in my ivory tower doing science. But I have found involvement in the mission, even over this very long period of time, an extremely fruitful stimulation for learning about new science. And so, in fact, even though data are not going to come back until 2016, I can assure you we will be working hard during that intervening period to prepare for the results. Of course, some of the results will be unexpected, as I said, but it's not as if we're sitting around twiddling our thumbs.
We have a question here on your right, folks.
I have to say that Juno takes a long time, but it's nothing like as long as New Horizons. We started working on the Pluto mission in 1989 for Juno, and we're only halfway there, and we launched in 2006. So, you know, there are long missions and really long missions. Similarly, Voyager, I started working on Voyager as a graduate student. And you know, it went past Jupiter in '79, and finally went past Neptune in '89. Is still going. So yeah, there's missions and there's missions, and we'll also, as we did with New Horizons, take some data along the way to test out the instruments, and we'll prepare and be ready for when we get there. But one of the key things that we do have to do is to document what we're doing very carefully, and train young people to be ready. So we have to anticipate the fact that there will be turnover in personnel between the beginning and the end of the mission. Yeah, good point.
Okay, we have a question here on the right.
Hello, Laurel Ann Whitlock from Orlando. I was just wondering, I believe it's 33 orbits that Juno is going to make. Is that the right number?
If all goes well, the spacecraft will make 33 orbits. It'll pass Jupiter 33 times, yes.
Why is that the number that they're going for?
Well, it has to do with those pesky radiation belts. Because what happens is the orbit starts off very nice and elliptical, with going pretty much crossing the equator out at 40 times Jupiter's radius and then skimming over the clouds. And then what happens, because of the fact that Jupiter isn't perfectly round, it's fat in its equator because of the spin. What that does is it makes the orbit begin to precess. So it goes from being oriented in the equator to dipping down. And then that means that this part of the orbit begins to dip into those radiation belts that are very close to the planet. So we have a sense of how long the spacecraft can realistically survive without being attacked by those radiation belts, the instruments being affected. And so we anticipate that at some point we'll have to send it into Jupiter. And the point, of course, is we have to send it into Jupiter so that it doesn't hit Europa. And you all know why we mustn't hit Europa, right?
Okay, we're going to do a quick mic switch here. Hang on. Okay, next question's back here in the back.
No problem. Hi, Tony Rice from Raleigh, North Carolina. Had a question I was hoping for anybody up there. Could you compare and contrast the kind of science that you're expecting to get both on orbit versus during that deorbit? What are you expecting to get during that deorbit phase?
Okay, during the deorbit, will happen very quickly. So basically it'll be exactly the same as the other orbits, but dive into the clouds and into the planet. I don't know how much data we're actually going to get. We will keep the particle data and the magnetic field data going, instruments going, but I don't think we're going to get anything particularly new compared with the ones that were just not hitting the planet, as it were. So we just want to get there, get into orbit, get a few orbits, and then we'll worry about deorbiting later. Who knows? It may be that the radiation is not as bad and we can last longer.
We got new batteries now, so hopefully it'll stop cutting out.
Hi, I'm Stephanie Lee from Minneapolis, Minnesota, and I'm just curious what happens from launch when it goes successful onto Jupiter. You said you test some of the machines, but what else happens?
Well, we have to do some maneuvers. So we have to, first of all, we have to get it out of Earth orbit, and so we're going to do that by firing one of the rocket. It'll get us out of orbit. Then we go out, and we go out past the asteroid belt, and we come back again and rendezvous with Earth. And we use that primarily to get a kick, a gravity kick, that will get us to Jupiter faster. But the other purpose is that we're going to sneakily, Jan Chodas isn't here, right? The project manager. Oh, she is. So we're going to test out the instruments by doing a little science along the way. So as we fly by Earth, we'll turn on the instruments, we'll take some pictures, we'll test out the various modes of operation, and we'll make some measurements along the way. And then once we go past Earth, we leave after that gravity kick. We'll do, you know, along the way, we'll see, we'll check we're going in the right direction and we're getting there, everything's okay. And then as we approach Jupiter, we'll begin to make a whole bunch of observations, anticipating getting an idea of how Jupiter's behaving. We'll be using the UVS and the GRAM to do that, as well as the particle instruments, the wave instruments, and the magnetic field. And for me, it just happens to provide a really exciting opportunity, because that capture orbit, which is a very long orbit, which will be on the dawn side of Jupiter's magnetosphere, will measure the magnetosphere responding to the solar wind. So the magnetosphere goes in and out by about a factor of 2 due to the solar wind going by, and we'll be out there measuring that effect and looking at the aurora at the same time. So it's actually a unique opportunity. And then we get captured into close orbit and do all the regular science orbits.
Okay, another question in the back on the left here.
Hi, Sean Cowan from Hicksville, Ohio. Yes, you all know it's a real town. Question is, now that we've had a chance to kind of all of us collectively be in the social media fishbowl, if you will, how do you feel social media has impacted your particular mission with having this Juno tweet up? And then social media in general. A second part would be, how do you feel it may impact future missions coming out?
Well, to be honest with you, very few in the science team tweet. I've never tweeted in my life, okay? I barely use a cell phone, and I suspect we're all a bit that way. But what I think is extremely exciting is that you're all here. We didn't have this with New Horizons. We didn't have this with other missions that I was involved. We certainly didn't have this with Voyager. So I think this is fantastic. Radio shows were all very good. TV was all very good. But this is a way in which it's getting out there quick and fast. You know, if I need some information about the Juno mission, I go to YouTube, I have to say, because I know it's there. So I think it is making a difference. Now, it's making a big difference for teaching, and we all teach. The three of us here are all teachers. And we teach at the university, and it's making a huge difference. We can get access to materials, and we can get it out and get it to the students. But I also have to say, it's been kind of interesting. I took some pictures of you all, because this is a bit like one of my classrooms. And there's a huge debate amongst us teachers. Why do we bother to be here if you guys are all out there doing your stuff out there? And so there's an interesting question about where we're going in terms of use of this. And what worries me, I'll be quite honest with you, is attention span. And I worry about deep thinking and deep reading and deep understanding and absorption. And if things move a bit too fast, quick and furious, you don't get that deep thinking that you need to struggle through a difficult problem, like doing the math to understand one of Dave's papers. You know, so there's good and bad, but basically really good. You guys want to comment?
Okay, do I start now? Twitter doesn't affect my life, actually. The trouble with having such good speakers is that when you're at the tail of the proceedings, there's not too much left to say, okay? But I'll try to decorate what people have said before. So let me start with NASA Jim, who was totally brilliant, and say something about methane, because I'm involved in that experiment, and so I'm worried about what the results are going to mean. First of all, methane from cows comes from burps. Cows are not jet propelled, okay? Second thing is, which is even less romantic, a lot of methane on Earth is generated by rice paddies because the bacteria that make methane love to live on the roots of rice. So, as the need in the world increases for more food, we're going to get more methane, okay? Kind of a sobering concept. Let's see, now we get to, one more thing about NASA Jim. He talked about what NASA was doing, and he left out one thing that's kind of dear to my heart, and that's the Cassini-Huygens mission, okay? I'd like you to think for a minute, because we tend to take all these things for granted, that the world, and that means the Western world, let's put the United States together with Europe, about 16 countries, got together, we sent a probe and an orbiter to the Saturn system. We deployed a probe to the surface of one of Saturn's satellites, okay? That's something that doesn't happen every day. And yet people are sort of forgetting about it already, which is part of the problem with progress, I guess. Anyway, that mission is still going strong and still producing data, and we love it a lot. Okay, we come to Scott Bolton, and now I can tell you how the mission got started. It got started in a JPL cafeteria, where I was innocently eating lunch, and Scott came over with this brilliant idea of having a probe in a polar orbit around Jupiter, which would give a much better or much different view of the magnetosphere than we'd ever have before. And he asked me, is there anything else we could do with the probe in that situation? And I said, oxygen, because I had just come off the Galileo probe, and as Scott told you, we hadn't been able to measure the oxygen. We saw a little bit of water vapor in the upper atmosphere, and so we know there was oxygen there, but we didn't get the global abundance of oxygen because that's tied up with hydrogen and water, and that's very low in the atmosphere, below the clouds that we could see, and below the region that the probe could get to. So that was a big missing link, okay? And what else? Anyway, it worked, and here we are. And it's a wonderful mission. And let me just say a few words again about these great ideas that Fran was just talking about. You can imagine our ancient ancestors standing out on the lawn here, on the savannah, let's say. They're looking into each other's eyes, they're looking up at the night sky, and they're thinking, what is all this about? And one of the things they're thinking, of course, is how did we get here? And another thing is, what's going on out there? Is there some connection between us and out there? And mind you, this was before NASA, okay? They had these ideas, they had these questions.
Before Twitter.
And before Tweet, yes. Actually, quite a bit before Tweet. Okay, so where do we go from there? Well, these ideas are so deep and so profound that they have actually influenced a lot of what goes on the Earth. They have influenced religions, okay, all over the planet. It's an important part of almost every religion. Secondly, they have influenced art, music, literature. And thirdly, they lead to a lot of wonderful arguments among scientists as to what the hell is going on. That's another question, by the way, a deep question, which people have had since the very beginning. Still going on. All right, so what's really happening? Oh, I forget these gentlemen and ladies. I should decorate them too. This guy is very hard to decorate, so let me just decorate him the way people get decorated in Washington by the president. In addition to showing that there was helium rain on Jupiter, he figured out this brilliant idea that neon, which had been missing, we haven't been able to connect to see it with the probe. It was, actually, we saw it, sorry, but it was very depleted. Why? Why was it depleted? Dave figured out that the neon, too many elements, the neon was dissolving in the helium rain and getting down inside. That was a stroke. That was a very nice stroke. I have a smaller decoration for Fran. Sorry for that. I was giving a lecture at the AGU one time, and I couldn't get the AV to work. It just wouldn't work. Fran got up from the audience, came up there, pushed one button, it worked. Which, the moral is, when you're in trouble, ask a lady, okay?
Can we make this the last few seconds if we could? Our next speakers are on a tight schedule.
I got a few seconds?
Yeah, if we could
Few
wrap
seconds.
up. I apologize.
Okay. Oxygen is a really good thing. It tells us about whether or not Jupiter migrated. We can actually deduce that. It tells us about a very important element for building interior models. We need it. We don't have it. And you're all breathing it, which is kind of nice. But here, mind you, it's produced by green plants, okay? It didn't get here from outer space. So be friends with your green plants. We need them. Okay?
So let's hear it for our planetary scientists, folks. Sorry to have to cut that short. I hope you're able to stick around a little bit and see if any of the Tweeps have some more questions for you here in the back. Thank you very much. Appreciate it. Thank you. Okay, so I'd like to introduce our next speakers. When I asked my colleagues at JPL how to explain how the Juno proposal manager and the Juno project manager fit into the story, they said this is an easy one. Because Steve Matuszek is the grandfather of Juno, and Jan Chodas is the superhuman CEO of the mission. So you get an idea in someone's head, it comes down to paper, these two help make it happen. So with that, Steve Matuszek, the Juno proposal manager, and Jan Chodas, the Juno project manager.
Volunteered to hold this for me for minutes. Can here hold this? Is that okay? I'll get back to you in a little bit with that. So I wanted to talk about some of the early days. We started working on the proposal in 2003. One of the big things we had to decide at the beginning was, of course, everybody knows that Juno spins. And we had to say, well, which way is it going to spin? And we scratched our heads and said, well, I don't know, maybe it should spin this way. And half the team said that, and the other half the team said, well, no, I think it should spin this way. So we scratched our heads some more, and finally we came up with the reason for the way it's going to spin. So if you're facing the solar rays, it's spinning this way. And the reason we do that is because we actually get a few more measurements at Jupiter, and every measurement is important. So that's the reason we spin that way. Another question I get, I forgot to mention to everybody, I'm the one to blame for why we're launching in August. So I'm sorry about that. We have to launch in August to get to Jupiter. The reason for that is that we launch, of course, and then we do a 2-year loop and come back to the Earth again. And people, again, they scratch their heads and say, well, why do you come back to the Earth again? Don't you want to get out to Jupiter? We have to come back to the Earth because I'm borrowing ever so little bit of energy from the Earth so that we can get out to Jupiter. We went on the Atlas V 551, and that's how we were able to fit the mission onto that launch vehicle, is do a gravity-assisted Earth and get out to Jupiter in 5 years. Another question I get a lot is why, when you're spinning, how do you point? Because everybody knows when you have a bicycle wheel and it's spinning and you try and move it, it's not easy to move sometimes. And so how do you point it? Well, the answer is we don't need to point it. The reason we don't need to point it is as things are spinning around, and you've seen all those science instruments that are on the side, well, they go by and they see Jupiter once every revolution, and so we don't need to point the spacecraft. And so it can spin and stay. It's very stable out in space. It floats along and doesn't really have to do much on its way out to Jupiter, and even at Jupiter. And the last thing I'm going to talk about here before I hand it over to Jan, and then I'll come back up probably here to answer a few questions too, is Fran, I think, talked about it when she was up here. She said she loved that huge orbit that we go into initially. And why do we have to go into a huge orbit like that, 107-day orbit? I mean, we get to Jupiter, we fire the engine, and why do we go into such a big orbit? Well, the answer to that is, in the original proposal, we did not do that. We went straight into the 11-day orbit. And then we needed to figure out how to reduce some of the mass. And so I scratched my head and I said, if we go into a big orbit, we're going to use less propellant. So we go into a big, huge orbit, and then we get down to our final orbit. after that one big orbit. So that's, again, saves some more propellant and gets more instruments and measurements back from Jupiter. So I'll stay up here now. I'm going to tag team with Jan and turn it over to her.
Thanks, Steve. It's great to be here today. Welcome to the Juno launch. We're planning on launch tomorrow, August 5th. This morning at 6:30, we met over in the Atlas Spaceflight Operations Center and got yet another weather briefing to decide whether or not to roll out today. And of course, Emily is being very fickle, not very easily predicted what is going to happen with this tropical storm. But the weather folks put their heads together and decided that yes, we can roll out today, and we'll have another meeting 6 a.m. tomorrow morning to decide whether we can go for the launch opportunity tomorrow. We'd like to have opportunities both Friday and Saturday, so we'll just keep track of Emily. It's traveling more westerly than they originally anticipated. It's not made its turn north. We really wanted it to turn north earlier so it would stay to the east of the peninsula. But right now, everything looks good for an opportunity tomorrow. Noting the time, I think it's a little after noon now, and our launch window tomorrow opens at 11:34 a.m., so we're less than 24 hours from liftoff. We have a 69-minute window tomorrow to attempt, and we have a 22-day launch period, as I'm sure you all know, with daily windows up to about 90 minutes most days. Right now, the spacecraft is in its stowed configuration on top of the rocket. So, unlike this model here that shows the beautiful arrays deployed, they're all folded up against the spacecraft. The spacecraft is about 11.5 feet high, about 11.5 feet across. But if you did a diameter of a circle from the tip of the mag boom all the way around, it's about 80 feet across. So it really is a large spacecraft with the wings deployed. So everything's ready to go. We're ready. The rocket's ready. The weather's looking good. And go Juno. So yeah, I can only stay for a few more minutes, so I'd be happy to take some questions before turning it back over to Steve, if there's anything that you'd like to know. Yes.
We've got first questions over here on the left.
Hi, Jan. I'll ask the non-science question here. As I know there's a couple project managers in the room, from a project management perspective on a very large project like this, what are some of the challenges you faced over the past couple of years?
Well, on a large project, as any large team, you want to make sure that you have really good team communication and team division of responsibilities and esprit de corps. I mean, you want to work. One of the things I take the most pleasure in is seeing a team evolve so that everyone understands their roles and responsibilities. Each person knows what they need to take care of, who their interfaces are. They work harmoniously. Mutual respect and integrity are important because you want to make sure that when you run into a problem, you can debate the pros and cons in a non-emotional fashion and make sure that you make the right decision for the best of Juno. Anything else?
Any questions on this side? Yep, one right here.
Because this is a Tweetup, I feel I'd be amiss if I didn't direct a question towards you from somebody I follow on Twitter, Chris Astro. And he'd like to know if, can you please extend the mission for more than just a year? Just make it a little longer.
Well, that's actually a better question for Steve from a mission design perspective. But any other questions for me from a project management perspective? The boring management, budget, schedule side of things. We are on schedule and on budget, so that's a tribute to the extended Juno team.
One question here in the back.
On that topic, a lot of NASA projects have had a tendency to get really far off of budget. So how is Juno different than, say, James Webb or the Space Shuttle or Mars Science Laboratory?
Well, we are on schedule and on budget. We have a total budget of $1.1 billion, and we're coming in a little bit under that. Thanks to the great teamwork and focus from everyone across the nation and the world. We have international partnerships as well. It takes everyone doing the right technical job and being sensitive to the technical scope, the schedule, and the budget to make it come off like that.
Questions? One here to your right.
Yeah, hi, my name is Patrick Kavanaugh. I was just wondering how you got involved with NASA originally and how you rose to be at the position you're at now, leading project manager for this mission.
Well, I joined the Jet Propulsion Laboratory in 1980, so I've been there over 31 years. When I was in, I'm actually Canadian. I went to University of Toronto. Any Canadians here? All right, Toronto, University of Toronto, aerospace engineering, bachelor's and master's degrees. And the space side of aerospace engineering appealed to me. The math and physics, predictability appealed to me in high school and college. And so when I was applying for a job, it's serendipitous and timing is everything. And I was able to get a visa that allowed me to come and work at JPL and join the Galileo mission. So I worked on the Galileo mission, the Attitude and Articulation Control Subsystem from 1980 through Galileo's launch. I ended up as the technical manager of that subsystem. But really, I think that I enjoy the technical topic of aerospace and space exploration, but my personal strengths are more in planning, coordination, management, scheduling, budget, that sort of thing, organizing, anticipating problems, early so you can work them out when they're small. So I think I naturally gravitated to be more a technical manager than staying in the pure technical field. And JPL has room for both. Thanks very much. I got to run back and do another guest briefing. Thank you very much. And once again, go Juno.
Okay, I remembered your question. The question, I'll just repeat it so people. Question is why not extend Juno's mission? Well, the short answer. I'll give the short answer and the long answer. The short answer is that Jupiter, of course, has very high radiation field, and as we go along in the mission, the orbit. I'm actually going to have to. Maybe you can stand up and hold the globe, like right about there. Thank you. You can help answer your own question. Okay, so if you're facing Jupiter like this, and the orbit is coming in like this.
You want me to do that? You do the talk and I'll do.
Go. Okay. So we're coming in like that. Excellent. 3D animation, and then. Well, that's the big orbit, and then we go in and we get into the smaller orbit. Now we're in. Now the orbit, though, Jupiter. Every time we go by, Jupiter's torquing the orbit down like this, so it starts getting more and more down, and we start getting more and more radiation as the mission goes along. So by the time we get to the 33rd orbit, we're getting pretty big doses of radiation, and we want to make sure that we can control the spacecraft so that we can put it into Jupiter at the end. You could do the final, it goes in. and so we might have the ability, if everything's going great, you could go maybe an orbit or two more, but that's about it because the radiation just gets to be so intense. Okay, I wanted to add about my background too, because I've actually been following some of the tweets on here because I have a Twitter account. I don't tweet very often, but one of the things I've seen is people who said, "Yeah, I want to work at NASA." Or they're in college now, they're about to graduate. Or I wanted to say that's what I did. I went to University of Colorado Boulder, and I said, "I want to work for NASA," and I was just persistent. I just said, "I'm going to do that." I got a job at JPL. I worked on the Voyager mission. When I was 25 years old, I flew by the planet Neptune, and now we're going to Jupiter. Those kind of dreams, they can happen. I mean, you set your mind to it, study the right stuff, and it happens. What I started out doing was orbital mechanics, and that's how I know how to get out to Jupiter and plan that kind of stuff. And once we're at Jupiter, let's see. I think there was another question. Let me talk a little bit about the orbit. Now, I wasn't totally honest when I said that we don't have to point the spacecraft. We actually have to point the spacecraft only twice. So I'm going to borrow the globe again. Sorry to. Okay, so if we're coming in like this, you've heard of the microwave radiometer. It comes in and it needs to be parallel with Jupiter. So that's one of our orbit types. And the other type is when we're going up very close to the planet, we do a gravity science because we get within about 3,000 miles, 5,000 kilometers of the cloud tops there. And so we're going to get, all the measurements are going to be awesome when we're that close. And when we're in that way, we point the high gain antenna at the Earth so we can do the gravity science. The Deep Space Network, actually the biggest instrument on Juno involves the high gain antenna and the telecom subsystem and the Deep Space Network antennas here on Earth at Goldstone, and that's the whole instrument. It takes the whole array there to sense down to 1 millimeter per second the gravity science as we're going by there. Later on, you'll hear some more about that too. That's less than an Earth height, right? Oh yeah, that's way less. That's about the distance that I flew flying here from LA above the cloud tops. So I'm going to pause for a second and take some questions. Thanks to the 3D animators too. That was really cool. I want to do that again sometime. That was awesome.
We've got a question right here.
Okay.
Yeah, your great 3D animation brought to mind a question for me. When you do deorbit, are you targeting a specific hemisphere, up northern pole, southern pole, equator, and would the inclination or the orbital mechanics be right for visualization from Earth?
Visualization from Earth, I'm going to have to do a quick 3D inside my head. The first part of it is it's going to come in up here around the pole. There's no choice. Since the orbit goes like this and we do the maneuver out here, the deorbit maneuver, it's going to make the burn and then come in and go in the northern hemisphere. I think it's so small. The Juno spacecraft is big, but compared to Jupiter, it's so small, I don't think we can see it. That's just a guess on my part. I'll have to go back. That actually put a thought in my head, so I'm going to go back and see if... I don't think we can, but that's a good question. I'm going to check that out. If we can see it, I certainly want to see that.
Steve, we have a question here, or a comment back right. This way.
Right.
Speaker to speaker.
Okay, for those of you who aren't rocket scientists, okay, if you get up at 5 o'clock in the morning, you can see our target right up here overhead, okay, in the eastern sky. So take a look. And if you've got 7x50 binoculars and you can hold them steady, you've got a tripod, it's even better, you can see the moons of Jupiter in the same way that Galileo did when he discovered them. So I recommend it.
Yeah, it's an awesome sight. I look through my telescope all the time. Other
questions?
Got one out here in the middle.
Hi, I'm Warren Levine. Being that you went to Boulder, and since you're in the profession you are in, did you ever enter a flying machine into that annual race they've got?
Oh, no, I've observed it a lot, but I never entered a machine there. Perhaps I should sometime. That would be interesting. Yeah, that'd be really cool.
Okay, time for one last question. Who wants it?
The speakers have talked about all of the data that's coming in, and I understand from a scientific perspective how useful it is, but on the team, have you thought at all about how to use that data in a way that the public can understand, visualizations or something that goes beyond just the pictures that are coming back from JunoCam? I guess I'm thinking of how data is really difficult for people to get, so how do you help the public get it in order to make them care about planetary missions like this?
I'm going to take a crack at that, and then I'm going to turn it over to probably to Fran and some others, but the answer is yes. There are going to be a lot of visualizations coming out because when I first started working on Juno, there's JunoCam, which is the visible camera, but everything else, magnetometer, gravity science, plasma, particles, your eyes can't see that, and so Juno is seeing it in different ways, and there's a lot of planning going into how to put all those things together and make them understandable to the science team and to everyone else too. But now I'm going to tag.
Juno is a little different from the other big missions like Galileo and to some extent Cassini because it doesn't last that long. So we have to be ready when we get there to analyze the data. So right now I'm training a couple of undergraduates and 2 graduate students to learn how to analyze the particle data. So we've got visualization tools ready to get those data out. We're also going to meet as a team next week, and one of the top priorities of the magnetospheric group is to put together how do we put all the data together and make them available and have them available on the web for people to look at. Just as the National Space Weather Center, which is in Boulder, Colorado, at the NOAA center there, they put out space weather for the Earth. So the magnetic field and the energetic particles that generate the Earth's aurora, you can go see them generated by NASA and other spacecraft. You can just go onto their website and see what's happening now in space weather. We want to do the same with Juno, Jupiter's weather, using Juno, so you'll be able to look at the Juno space weather, Jupiter space weather, same way. So this is the new way of doing business. Just like Twitter, we're growing up finally and making it available to the taxpayer.
Okay.
Oh. We can do one more quick one because I see our next speaker hydrating over there, which is a very good idea, and I encourage everyone to keep doing the same. So how about one quick question? Right here.
Hi, Don Schwartz, Ishkabibble. The question is it keeps on coming up about the duration and the lifetimes of the people involved in the long projects. Well, is there a way, short of using gravity assist, that we can bypass gravity assist? And how fast would the spacecraft have to go substantially cut down the time of these missions?
The way, well, let me use Juno as an example. In the early days, we looked at could we go direct, and that would take 3 years to get to Jupiter. And so it comes down to a bigger launch vehicle for less, you know, if we had bigger launch vehicle for the same price, we could, like solar electric propulsion and those kind. For this kind of mission, it doesn't really help that. Like, I mean, the Dawn spacecraft is now at Vesta and it's orbiting, and that's the reason it got there is with solar electric propulsion. For going out to Jupiter, we're going so fast anyway to get out there that solar electric propulsion didn't really help us. But we looked at that early on to see if it would help. So like solar electric, I'm a big fan of electric propulsion. So and that really works for rendezvousing with asteroids and things that don't have much mass, but Jupiter has so much mass that we're using that to our advantage when we get there, so it's helping us stop and get into orbit and things like that. So, good question.
Thank you very much, Steve. Thank you. Okay, we're coming to a close just about on the speaking portion. Our final speaker today is Chris Brocious. He is the Chief Systems Engineer for Juno for Lockheed Martin, and he can tell you a little bit from an engineering perspective how the heck this remarkable spacecraft came together and how they built it. With that, Chris.
Thank you very much. This is really a great opportunity. I want to share some interesting facts, engineering. Hopefully you guys are interested in how we put the spacecraft together and what it's made of and how it all works. The spacecraft was born in Denver at the Lockheed Martin facility. That's where we build all of our planetaries. And a couple of things I want to point out. We've all seen how big these solar arrays are, right? There's 18,600 solar cells on there. And I have one here if you want to take a look at it. It is a very high efficiency cell. It's a triple junction cell. And we actually had almost twice as many of these things built so we could cherry pick them to get the very best performance for this mission. You guys might have heard that out at Jupiter, the sun isn't very bright. And the solar arrays produce about 450 watts normally over the course of the mission. That won't even run a hairdryer. You know, that won't even power those lights over there. So we had to design the mission to be very electrically efficient. We needed the most efficient solar cells we could. Conversely, those big arrays here at Earth, they produce almost 19,000 watts. That could power a couple of houses easily. So you kind of get a perspective of the change that Juno goes through. We also had to design the power system so that when it's close to Earth, we're not generating that much power, because that would blow the batteries to pieces, it would fry all the electronics. So we had to make it very smart and very sophisticated so it knows where it is with respect to the sun, and it knows how much power to turn on and turn off. Another thing that's really interesting about this particular spacecraft is this block underneath the high gain antenna here called the vault. You guys have heard about what a wonderful place Jupiter is and all the secrets that are there, but I'll tell you, from an engineering perspective, it's also really nasty. The radiation is just unbelievable. It's a unique radiation field, mostly dominated by electrons. And it posed some very interesting engineering challenges for us, because we had to figure out how to shield all the electronics in there so they would survive that. Steve talked a little bit about how at the end of the mission we've accumulated as much radiation as we can tolerate. That is absolutely true. The vault, as it stands right now, is made out of this material here, titanium. Titanium is a very nice material for this because it's got some excellent shielding characteristics. The vault is very much tailored because we are so weight conscious. Some of the panels are 1/4 of an inch thick, other ones are 1/2 an inch thick, depending on what's around them, and will take advantage of shielding. But overall, the vault produces about a factor of 4,000 in radiation reduction. So it does an outstanding job at protecting our equipment in there. We originally, back in the days when Steve was working the proposal, had thought that we were going to use a material, tantalum, tantalum sandwich construction for the vault. Very much like this material here, tungsten. It's very dense, very heavy, also has some nice characteristics. But we realized when we started designing and figuring out how we're going to build the vault that it's hard to glue things to tantalum. We can't do that very well. And in the nasty environment of space where it's hot and it's cold and vacuum, we didn't have any qualified processes that we could trust to use that material. So right before our critical design review, we switched to titanium, which is one of our favorite materials, and we know how to use it. It added a little bit of weight overall, but it was the right thing to do. The spacecraft is big. You've heard about it. It's 3,625 kilograms. About 2,000 kilograms of fuel. That's about 500 gallons of propellants total. For those of you that are interested about the environment and things like that, we have figured out our miles per gallon on Juno. It's almost 3.8 million miles per gallon. So it's pretty good for a hybrid vehicle, yes? And then finally, the last thing that was very challenging about this radiation field, it's definitely one of the most strongest engineering nemesis you can think of, is that because it's electron species dominated, it acts a lot like people do with wool socks on running across a carpet in the wintertime. It generates a ton of static electricity. In fact, it generates so much electricity that if we didn't do something, we could get tens of thousands of volts of discharge within the spacecraft itself. All the dielectric materials, the materials that don't conduct electricity, the electrons lodge in there and they stay in there, but they don't like to stay in there once they get too crowded, and they discharge like a static shock like you get in the wintertime. We couldn't tolerate that, so we had to design and build a spacecraft to give a path to everything for those electrons to escape, so we couldn't get that type of potential. And that turned out to be a big engineering challenge. The Atlo folks that actually built the vehicle, they hated us because we made them run ground wires all over the place and shielding and use special compounds that are conductive. We actually are using carbon nanotubes to coat the thruster towers here. That turns out to be an excellent material for that because it's conductive, it's very strong, and it turned out to be very nice. So we actually have some state-of-the-art technology in there as well. Do you guys have any questions? Yes.
Mics are coming.
So this one first. You mentioned the vault gives a 4,000 times attenuation of the radiation, and my question is, first of all, is that enough? And secondly, how do you simulate that environment for testing?
That's a good question. First off, yes, it's enough. You know, engineers by nature are very conservative, and we never like to to cut it right on the edge. So we have a radiation design margin of 2. So we actually only need a factor of 2,000 based on the components that are in there. To simulate and test that is very difficult. We have not put the vault in a chamber and bombed it to see what comes in on the other side. That's all done analytically. We do test all the individual components, though, representative samples, lot accepting test of radiation, so we know what pieces can tolerate, so we know how sensitive they are. And then we've used some very sophisticated computer modeling tools to simulate the Jovian radiation, its impact on the vault, what gets through, and what that does to the individual pieces. So that's how that's done. Excellent question.
Chris, while we're taking Q&A, did you want to pass the samples around?
Oh, sure.
Is there a way that people can see them?
Absolutely.
Okay. We'll give you a hand.
Here's a solar array. I do need that back.
Please.
And then here is some tungsten, aluminum, and titanium. Again, aluminum and titanium are pretty common for spacecraft. The tungsten's a little bit different. It's very close to tantalum. You see how dense it is.
So we've got our next question over here on the left.
Yes.
Hi. I've actually got a question from one of my Twitter followers who I moderate some Ustreams with. He wants to know how many of the solar cells you lose during the mission and the types of failures you'll see, and if it hits anything on the way.
We're expecting to lose somewhere between 5 and 10% of the cells. Some of them just die because of age and attrition. We have cherry-picked them to try to get the very best ones. We also lose a few to what's called micrometeoroids, the little bits of dust that are in interstellar space. And those things actually can impact the glass and etch the glass and lose the cell that way. We may also take a break in one of the wires by one of these micrometeoroids. So we do plan to lose some solar cells. We do provide extra power capability for that eventuality so that after we have lost the cells we're going to, we can still get the mission done.
Question here in the back?
Yes.
Space-rated electronics tend to be pretty old, so like what is the power levels of the computers on here like compared to, you know, a modern personal computer kind of thing?
Actually, our flight computers are very modern. They're PowerPC based. It's a radiation hard chip called the RAD 750, and it's very comparable to what's in a Mac right now. The overall flight computers use about 30 watts of power, each one. So they're not, you know, overly constrained. We actually do have a lot of state-of-the-art electronics in there now for a couple of reasons. One, we need the radiation tolerance, and you need that for this mission more than anything else. And two, because the mission is so long, we need high reliability parts. We need to make sure these things are going to last and not fail before the end of the mission.
Question here on the side?
Yes.
What is the what kind of fail safes have been put into the spacecraft in case something catastrophic goes wrong? I mean, we had problems with the Mars rovers where it basically just went to sleep, and we kind of like hoped that, you know, the system would basically restart itself. I mean, if we completely lose everything and Juno vanishes, what is it going to do to become self-aware and Skynet and all that stuff?
That's an excellent question. This spacecraft is designed to take care of itself. It's almost self-aware. It's not got artificial intelligence on it, but it does constantly monitor its health, its status. We have whole pieces of software and whole chips that do nothing but make sure that the spacecraft is okay and that everything is working the way it's supposed to. It is what we call dual string design, so it has 2 complete sets of avionics. The sensors are cross-strapped, so computer A can talk to the star camera A or B, same thing with the inertial measurement units. Everything's cross-strapped so that if you have an issue, the computer who is currently running can talk to all the other components on the spacecraft. We also have a pretty neat setup that has been evolving for our planetary spacecraft back from MRO all the way back to the Magellan days, where if one computer gets in trouble, the system is designed to take that computer off and bring the other one up, and the other one comes up in what's called safe mode. And that's a very happy place for the spacecraft, where it just sits there, it goes to a minimum power, it points to the sun to make sure that it's got lots of power available, and it waits for the ground to come in and figure it out. And that's really important for this mission. Because if something does happen to Jupiter, it takes the spacecraft an hour for that information to get back to Earth because of the one-way light time. We're that far away. You just can't get your head around how far that is. So when the ground sees a problem, it'll take the ground guys probably a few hours at best to figure out what to do, and they send some commands up. There's another hour just to get back to the spacecraft. By that time, the spacecraft could have been long dead, and that's something that we don't want. So we've purposely designed this thing to take care of itself, given it lots of redundancy and the fail-safes that it can jump to the other side if necessary.
Let me pause to see if there are any questions on that side. Nope.
We got one right here.
Yep.
Hey, how much and what kind of engineering data is sent back at a regular basis? And is it constantly sent back? Is it sent back in packets every couple of hours?
The answer is yes, yes, and yes. We have almost 30,000 individual telemetry parameters that can beam back from the spacecraft. We monitor everything from temperatures at the end of the instrument boom to how much utilization is being used by the computer at the time to the individual states on the battery cells. There's a pretty sophisticated system inside which takes all of these measurements and beams them back at specific intervals and specific frequencies. Some things we're much more interested than other things because they change slower or perhaps it's more important. Temperatures generally come back once a minute because temperatures just don't change that fast. During the middle of a burn, you're really interested in delta V that's being accumulated. We'll send that back at 100 millisecond intervals. So it really depends on what part of the mission is, what's going on, and what instrumentation is important. The telemetry system is also programmable. So if we see something, we learn something about the spacecraft while it's in flight, we can change what information comes back. We can change how fast it comes back in case we need to look at something or something else or something more frequently. So it's very flexible.
Okay, question here in the back. Back right.
Oh, sorry. Hi. I have a question about, we all are kind of aware of the rich history that NASA possesses with space probes from Pioneer to Voyager to the more modern missions. Is there anything specific you can think of that you may have learned from previous missions to Jupiter that you can apply to lessons learned for Juno?
Oh, absolutely. The easiest one, of course, is Galileo, because Galileo gave us some very good radiation data about the planet. It didn't get as close as Juno's going to get, but it gave us an excellent idea of what to expect when we get there radiation-wise. Some of the other missions that we've flown, Odyssey, MRO, Stardust, we've incorporated numerous lessons learned from them. Everything from the type of battery we use. We're now using a lithium-ion battery on this, as opposed to NiCads, which were used back on Magellan and in the old days, if you will. Computer software, that's constantly evolving. We've been evolving essentially the same core set of software from, again, the old days of Magellan, if you will, all the way through up and into this bird now. And the stuff that is in Juno now is being constantly involved, lessons learned for the next missions coming up, such as Maven, as an example. The Grail spacecraft that are going to launch about a month after we do, we share a lot of common software with them as well. So yeah, we're always trying to learn from the missions that have gone in the past and how to fit that into the spacecraft, especially the lessons learned when things don't go so well.
Okay, question over here in the middle.
Hi. In terms of engineering the spacecraft, what did you expect to be the most challenging aspect of it? Did that actually turn out to be the biggest challenge, and how did you handle it?
Wow, there's so many of them. One of the biggest things that we started looking at right away was back in Phase B. Right on the side of the spacecraft here on the upper deck, we have these two cameras. They're called stellar reference units. And their whole objective is to figure out where we're pointed in space. And they do that by looking at the stars as we're spinning by. And we can figure out where we're pointed in time based on the star pattern that we're looking at. To make that work for a spinner is a lot more complicated than making it work for an inertially stable spacecraft where it can stare at a constant sky all the time. And the thing that really makes it difficult is that stinking radiation field again, and what that does to a CCD or an active pixel sensor like you've got in your video camera or your cell phone camera. If you look at what the radiation field does to a typical camera, it looks like you're looking at a blank screen on the TV. It's just the fuzz and the noise is just unbelievable. So we had to work very hard to figure out how to filter that information while the whole screen is moving, while these stars are streaming by, so we could actually identify real stars as opposed to the noise, so we could come up with our attitude solution so we knew exactly where we were pointed. And of course, that's critical to folks like the magnetometer that are trying to map the magnetic field very accurately. That turned out to be one of the hardest initial challenges, and thankfully I'm able to report that it's actually working very well, and we expect the star cameras to have better performance than their requirements because it was worked so hard. So that was good.
Chris, let's do one more if you can stick
Sure.
around. Okay. How about right here in the back?
Being that Jupiter is so reflective, will Juno be able to gather light for its solar panels and use that electricity?
No. We're actually pointed in such a way that the solar panels aren't pointed at Jupiter. There is some albedo effects, and again, they do affect the optical experiments and they do affect the star cameras, but because we're spinning, we're not always looking at Jupiter. But for the most part, if you're the sun, the spacecraft is pointed like this at the sun, at the Earth, almost the whole time, and it goes around the planet. Where's Fran? And it's always pointed in that direction, so it never stares at the planet per se.
Okay, let's have a big round of applause for Chris Brocious.
Thanks, you guys.
Samples. Or Chris. Please find Chris. You've got the titanium and the solar panels. And yeah, what samples? So that's going to wrap it for today's speaking portion of the live webcast event. We want to thank everyone for being here with us. Big thank to all our speakers. If we could give another round of applause. And thanks to everyone who joined us at home. We encourage you to keep continuing the conversation with us at www.twitter.com/NASA Tweetup, following the NASA Tweetup hashtag as well as Juno. And we hope you'll be watching with us tomorrow. We're all excited about seeing a launch. The window opens at 11:34 Eastern tomorrow, August 5th. So we hope you'll be watching along with us on nasa.gov. And if everybody in the tent could just stay, we have a few announcements. And thank you all at home. Go Juno!